Okay, everyone, welcome to week 18 of quantum. No, am I wrong, Janice? 19?
I thought it was 19.
19, okay, you know, but oh no, it is 19. It is
19. 19.
Today is going to be sort of like a weird day because we're going to have to finish up last week. So we're going to finish the week interaction today. And I'm going to talk about, gosh, it's so weird lecturing with a hat. It's so different. I feel like, I don't know, a magician or something. So we're going to talk about the weak interaction. We're going to finish up the weak interaction because we still haven't defined all of the different interactions we can get. So that's an important thing we need to do. And then after we do that, I want to talk about non-abelian gauge theory, the Feynman rules. I want to give you the Feynman rules because I want you to do a little exercise with F cubed. You knew it was coming, so. And then, so that's not going to take too long. I'm literally going to write down the rules, and Srednicki has them, but I'm going to give them to you in a different gauge. And then once that's done, I'm going to finish off by briefly introducing you to a topic in quantum field theory called anomalies. Anomalies are a very rich subject, and I'm not going to be able to cover all of it today. I'm sort of going to set up the problem for next week, and next lecture will mostly be on anomalies, okay? Because there's a few interesting pieces of that. Okay, so we have 3 weeks to go this week, right? That's what I said, right? This week, next week, and the week after, and we're done. Next week, I'm going to spend the next 2 weeks maybe talking about special topics. So whatever you guys want, strings, if you want the basics of strings, if you want supersymmetry, whatever you want, I can talk about the next 2 weeks. So you tell me, or you tell me tomorrow what you want, because it's kind of wide open for the next 2 weeks. Okay, if you want to talk about strings, I have plenty of material. So because I just took 2 semesters of it. Okay. Great. Any questions from last time? No? It was all okay? Okay. Okay, let's get started then. The basic idea from last time was we wrote down, so the big takeaway from last time is what? We wrote down one Lagrangian, right? Within it was electromagnetism and the weak interaction. Okay, and from that, what did I show you last time? Did I show you the massive bosons? No, right? I just showed you the coupling to the Higgs field, right? That's where we ended. Okay, so, and we know it couples to a Higgs field. Okay, that's the big takeaway. Now, what are we looking for? We're looking for interactions. We want to know what kinds of interactions does this theory predict? And we want to see where the photon went. That's the question, okay? So let's begin by answering that question. So let's first predict the massive gauge bosons, okay? That's going to be the first goal. Let's see how we can do that. Okay, so let's begin by writing down this product. And this is going to be important to set us up using the language of the excited Higgs potential. So if I take this inner product using the excited Higgs potential, another word for the excited Higgs potential is what? The spontaneously broken, right? Higgs. That's probably the better way to do it. And this is just recasting it in the language from last lecture. If you took this scalar product, e squared v squared over 4. Again, the h of x and the v come from my definition of the minima, which was a bit scandalous, but we'll get there. Right, and we had some we had a lot of random gauge fields, But I assure you that this is sort of, this is the right way to think about it. Or this is what all the books call it. We're going to call this W mu1 squared. Okay, you're already starting to see W and Z, right? It's gonna come up. This is how everyone calls these things. And we'll call this G squared V, well, we won't call it. It is G squared V squared over 4, W2 mu squared, right? So when you take this inner product, you're gonna get two components of W, right? That's the basic idea. And then of course, you have to get the third component. So plus, can I factor something out? I don't know. Yes, I can. So V squared over 4. But then what goes inside? G W mu cubed minus, we'll call this G tilde B prime mu, because it's a coupling associated with the other gauge field, right? Squared plus higher order terms. That's what you get. Okay, and we see something kind of nice. First of all, we now have a term that goes GW mu or GB mu. Okay, that should immediately tell you something good. That means we have a coupling to a gauge field. Okay, and that immediately comes out in this inner product. So now, and also another thing to note, these gauge fields are massive gauge fields, right? They have a dependence on the coupling. So that is a distinct difference from QED, right? You know what, I'm gonna take this off because it's not sunny enough. That is a distinct difference from QED, is it not? Because in QED, we get a gauge field, right? We write down the covariant derivative and we get a gauge field that goes what? I.e. Q minus A mu. And the A mu is not coupled to anything, okay? It's totally on its own. So that's the big takeaway from this. So W mu1 and W mu2 are vector particles, right? They're described by a vector field or a gauge field, and they're massive. That's the first big takeaway just from doing this little inner product. Okay, and we can write down the mass. So what's the mass of the W? Can someone tell me? Or M squared? What would the mass be? It would just be G squared, V squared over 4, right? Defined by this parameter V. It's just some arbitrary thing that comes from the spontaneous symmetry breaking. Okay, also note that this linear combination, so first of all, this is associated with what? This is associated with W1 and W2, correct? Right, but also note that this linear combination is massive, but it's associated with a different mass, namely V squared over 4. Okay, so we have two other massive gauge fields with a different mass. Okay, and so now we also have two coupling dependencies, G and G tilde, which we know that is the coupling strength exactly the same for the W and Z? No. Okay, this is a bit artificial, right? Because I have demanded that G tilde is a different coupling, right? That doesn't sort of come out of the theory naturally. So like, let's just take a pause here. This is a silly exercise, but it's so important. What is the machinery that has created massive gauge fields? How did we get massive gauge fields in the theory? Can someone tell me? Yeah, how is this theory uniquely different from QED? What have I done here that I did not do in QED?
You have the Higgs field.
Yeah, that's correct. But then what did I do to it?
You broke the symmetry.
I broke the symmetry, exactly. So that's why this is called spontaneously broken gauge theory, okay? Because that is what makes this unique. If you don't spontaneously break the symmetry of a scalar field, you will not get massive gauge fields. You will get massless gauge fields, and you can describe QED. Fine with that, because the photon is massless. There is no massless gauge field that appear here. Okay. So the photon degrees of freedom are kind of suppressed in some sense. That's fine, because we don't have photon interactions in the weak interaction. There's no photons being exchanged in weak interactions. That seems a little bit of a cop-out though, right? Because if you say you want a unified theory, maybe you want the photon degrees of freedom implicitly there. But then you ask yourself, like, can this is not a Lagrangian, can such a Lagrangian describe QED? The answer is probably not. You're probably still going to have to parse it out. And in that process of parsing out, you're going to get back to QED Lagrangian that you would have originally written down. You see what I'm saying? You're going to take particular pieces of that unified Lagrangian anyway. And in that process, you're going to recover that original thing. So in principle, yes. In practice, it's not really a big deal. Okay, let's continue. Right, so in the language we've been using, these are the Goldstone modes, right? This coupling to the W and B, whatever you want to call it. They're Goldstone modes, okay? And so these Goldstone modes, these three massive Goldstone modes will give rise to the W plus, W minus, and Z naught, the three gauge bosons of the theory. How are G and G tilde related? Does anyone know? It's our mysterious parameter. So G and G tilde are related by an angle, okay? That's how I can get to the different couplings. So if I draw a triangle, this seems so random, right? It's kind of crazy, like the fact that this random parameter relates different couplings. That's kind of nifty. In fact, I'm really curious. I should read Weinberg's original paper. I'm curious, like, how he figured this out. I certainly don't see it. And so you have an angle theta, you call that W, right? And if this side is G and this side is G tilde, right? Then very simply, right, tan theta W is equal to G tilde over G, right? So that's how they're related, the ratio between the two. It's related by some angle. This seems arbitrary, but actually you can get to the different couplings using this number. And one day Jenna and Isha will write a paper that derives this. But as of now, we don't know. It's some random parameter in the standard model. It's a very crucial parameter in the standard model, okay? It's sort of what this whole theory relies on. Okay, so this theta W is the so-called Weinberg angle, for those of you that want to Google this later. It's the Weinberg angle. Okay, so now I can put all of my interactions into a sort of matrix form with all of the different gauge fields. We can even put in the photon field, no problem. It's just not gonna have any stake in the game. But you can write down this whole operation in terms of now the Weinberg angle. So I have Z mu A mu. Okay. So I can write down a matrix equation that takes me between different different couplings, which in essence take me to different interactions, which in essence take me to different gauge bosons, right? That's the name of the game here. So I would have like cosine theta, I might get this wrong, sine theta W, oh my God, there might be a factor of a minus sign. We'll say this one's minus. Do check that because it could be wrong. Okay, W mu 3. Okay, that's the little matrix equation. And so now if we work out the same thing, d mu phi dagger d mu phi, what are we going to get now in terms of this? Because now remember W mu and B prime mu, sorry, yeah, W mu 2, W mu 1, and B mu 1, and W mu 3 are all related by this Weinberg angle. I don't know how we derived this. This is kind of crazy to me. I really want to know now.
I looked it up. The negative sign is on the other sign.
It's on the what? Okay. Right. There we go. Sorry. I knew I got that wrong. Okay. Okay. And what you'll find is you'll get this term, you'll get this term, you'll get this term. Okay. When you do this thing out. So you'll get the first 3 terms. Okay. So I'll just write first 3. Right? So I'm gonna have to rewrite it. Oh God, then what? Wait a second. I have to, doing these is a little tricky in your head. You have to just make sure. Right, you'll get G squared V squared over 4 cosine theta W. No, squared. Z mu squared plus however term. So you'll get this extra term dependent on Z. By the way, what is this? If you look back at your notes from 2 weeks ago, this is exactly what I wrote down for the Z mass. And then when you look back at your notes, tell me what V is. Okay. So so we've derived the masses, which is what I promised a few weeks ago. You see, like the more you do this, the fact that this works is so insane. It's so insane. It's really insane, honestly. It literally makes there is no reason any of this should work. That's why like only people who do physics really understand how crazy it is. People on the outside think we're doing something very, very precisely. We are and we aren't. Okay, the fact that this works is crazy. People don't seem to realize that, but okay. Okay, let's write down some interactions and then we'll be done. So I'm going to draw all the vertices for you. I think LB has these. I took them from Peskin-Schroeder, these diagrams. So I don't know if LB just put them in. Okay, I figured out something because now I spent some more time with LB because I have the book. They've taken a ton from Peskin and Schroeder. So if you really want like the upgrade, I think first go to Peskin and Schroeder. I think that nothing wrong with that because they've made it simpler. That's the whole point of the book. But a lot of the notation and it's all the same as Peskin and Schroeder. So if we overlap, it's because I'm using Peskin and Schroeder. So I don't know if, well, mostly for some stuff. Like this, I'm using Peskin and Schroeder. And I mean, I looked at LB. It literally looked the same that they took the notation. So I think the added value of the book is the writing. I don't know, probably. Because, for example, for the non-abelian, the anomaly stuff I'm going to show you is just my own notes, not from any book. So some of the topics are, it just depends. This is a very random subject, so I don't know what to tell you. Okay, everyone okay with all of this now? So a little less mysterious about the Weinberg angle, I hope. Okay. Okay, let's draw out the interactions. I wrote them down because I'm not going to remember them. See, that's the beauty of being a physicist. When you're working out a calculation, you don't need any notes. And when you have a bunch of things you need to memorize, great, you can just write it down. Isn't that great? Okay, so here are the interactions predicted, and I'm going to show you where these come from then in the Lagrangian. Okay, so the first one, well, we're going to have how many? 1, 2, 3, 1, 2, 3. One, two, three, four, 6. Okay. Peskin and Schroeder has these, so. Although I find in lecture, when I write them down, it's good because I almost never go back to the book and look it up. So. Okay, so we're going to have a typical photon interaction. I know I said it. I mean, this is not a weak interaction, right? Per se. This is just an electron going to an electron. And I said that the photon field was suppressed. Okay, I'll bring it back alive, don't worry. I'll bring it to life. Okay, next kind, we can have a right-handed electron. So with this chirality, and the intermediary is a Z. Okay, similarly, we can have a neutrino. Right, bar, intermediary is a Z. We can have a left-handed electron going to an anti-chiral left-handed electron. Intermediary is a Z, right? We can have a left-handed electron then decaying into its corresponding neutrino. And then the intermediary, I'm not going to use this. I'm just going to use a zigzag W plus. And we have a neutrino then going to the electron, the corresponding anti-electron, W mu. Nice. So this is basically all the predictions of the theory. It's kind of great that we can distill this into some simple picture, right? The best way to think about it is lepton to neutrino or quarks. Quarks also, right? As you should know by now, we probe quarks with the electromagnetic and weak interactions. That's how we really have learned about quarks. Basically, no experiments have been done really to test the strong interaction directly. It's not really something we do. God, it's such a pain to get Feynman diagrams in LaTeX. I was trying to put a few of them in our document and I gave up. It was painful, honestly. So I said, you know what, I'm just going to write out the equations. I'm going to go Schwinger style here and not bother with the Feynman diagram. Okay, can I erase? And then Isha will ask me, Kyle, why are these the interactions? And to that I say, take a philosophy class. Okay, so what is the best way to see the interactions in the mathematics? we write out the Lagrangian, right? That's the whole idea. And just like, remember, in QED, the process of minimal coupling allowed us to see the interactions in the Lagrangian, right? When you wrote things out in a gauge invariant way. Similarly, when we write things out in a gauge invariant way here, we should see some interactions. So let's write down the gauge fixed Lagrangian. Okay, we're going to pull out one term. So let's say we have something that goes I, R bar. I'm pulling out one term. Remember, the Lagrangian is much bigger than this, but it's not really. You can do that analysis on your own of the other terms. Gamma mu. D mu plus I G prime B mu. R plus I L bar. Gamma mu D mu. Now I need that SU2 piece. That's why. Minus I over 2 G tau. Right. That's just the SU2 piece. Dot W mu. Right. So the W and B fields couple in an SU2 fashion. Plus I over 2 G tilde tau dot B mu. Okay, so I will give you a quick second to pull out an interaction from this. So basically that involves writing things out in terms of Weinberg angles, right? So yeah, take a minute and think about it. And then I'll start writing it down slowly. It's okay. Isha's taking complex analysis next term, so she'll do all the contour integrals for us. I'm sick of them. Okay, I'll start slowly writing it down while I will think about it too. Okay, so right off the bat, I know I'm going to get this term. Right off the bat. Oh my gosh, this is annoying. Well, once you get the first thing in, it's easy to get the rest. It's just the prefactors that you have to worry about a little bit. I'll use the convention here that E just equals the sum of the chiral electron fields for that first term. Technically, you should write it out in terms of chiralities. Okay, let me think about, there's some prefactor here. I can't remember, just give me a second. Oh my gosh, I'll figure it out once I write out this whole term. Yeah. I think G over root 2. Okay, I think that's right. Okay, we're now, the magnitude of E is G sine, or the electric charge, whatever you want to call it, or just, yeah. Okay, let me make sure, wait. So yeah, this goes to this, but wait. Whoa, okay. Remember, R and L are, L is a doublet, right? You remember that, okay. That's where I'm getting the E's, the VE's, and the EL and ER from. That's good, right? So it's not that hard, it's just, okay. But the only hard part is these sines and cosines. That's the only hard part, because you just have to remember, and that's not even hard, it's pretty trivial, but when you're doing it from scratch. Okay, this is right. So can someone give me some ideas of the interactions now? So yeah, this is good. This is, Isha, are you okay with this? Or do you want me to quickly explain how you can get this expression?
Can you quickly explain?
Right, so that's fine. So remember, we defined capital R as ER, and we defined L as a doublet that went EL, VL. No, wait, that went EL, VE, right? Because neutrinos are only left-handed. So you use those definitions and you multiply everything out and you'll get this expression. And then use the depth, and then, so you need this, okay? So that should help you see where I got these E's and I got the VE's and I got all that. And then you use the definition that, what was the Weinberg matrix? You use the matrix equation you wrote for the Weinberg angle. I forget how it goes. You want me to remember again? It will use brain power.
I'm just gonna find it.
And you put those two things together and you get this. So this is really, so this is why I tell you this is very nasty, because this is only one piece of that Lagrangian. Now you imagine writing everything out, you're gonna get a mess. Okay, so can someone now elucidate some of the interactions for me? Well, that's what I want to know about, so. So A mu, so the photon only couples to the electron. That's the first thing. That's important. That's good. And what you should do as an exercise, you should get all of the different vertices we just wrote down from this term. It's just simple. So like, let's take one of them. Yeah, let's take one of them. So let's look at this term. So here I have an E bar L, right? And an EL and a Z mu, right? Because this is multiplied by these three terms, right? That means I'm going to get a vertex with an E bar L, EL, and Z mu. Make sure I drew one. It also means I'm going to get a vertex with a VE, V bar E, and Z mu, which we drew. Yeah? Okay, so those are the interaction terms. And it also means I'm going to get a Z mu, E bar R, ER. Yeah? Okay, so can someone else read off an interaction to me? And please don't say quarks. We're not there yet, so I don't really know where you're going to get that from. just read one off. It literally you have to read off the term, like what's coupling to what. It's explicit in the term, not implicit, explicit.
The left-handed electron and the electron neutrino coupled to the W boson.
Exactly. Good. Okay, so there you go. So minimal coupling allows us to see the terms, albeit we have some complicated stuff, you have to work out algebraically. Okay, can you erase? Oh, one quick note about discrete symmetries. Okay, so we have our three discrete symmetries. Well, I'll erase first. We have our three discrete symmetries. Charge conjugation, parity, and time reversal. Now, we have seen combinations of these symmetries violated in nature. We've never seen CPT violated. So CPT we think is a symmetry of quantum field theory. The weak interaction violates parity. That was the big discovery, right? So basically what that means, I just want to say this statement sort of in the language of a few weeks ago. It just means that parity, the parity operation is not a symmetry of the Hamiltonian density. So this does not leave the Hamiltonian density invariant. Okay, that combination, that's what it means mathematically. Okay? Okay, that's the weak interaction. So anyone have questions? Or we kind of spent a few weeks on it. And my goal was to first just calculate Feynman diagrams with you, which is what we did. And then to show you sort of where all the rules come from, and which now we know. Axial vector, all that. It's all in the framework, the mathematical framework. And we see that the weak interaction makes very nice predictions. Or not the weak interaction. The unified model makes nice predictions. Anyone have any comments or questions before we go to something totally unrelated?
In the last term, like the stuff that was in the square brackets, the first term inside of that, it was like JE gamma mu, EL W mu. But the only W mu interactions that we wrote down were between like an electron and a neutrino. So what would that interaction be?
Sorry, can you say the term again?
JE gamma mu,
J?
EL, yeah, J.
You mean V?
Oh, that makes a lot more sense.
Right? There should be no J.
I thought that was a J. That makes a lot more sense.
No,
Okay.
there should be no
Yeah.
J. Okay, sorry. I tried, technically that's a new, so I tried to, okay, there should be no J's. I don't know
Okay, cool.
We're not Yukawa predicting the J meson or the J psi or whatever he predicted. Okay. See, that's good, right? So now you can check the theory. That's good. That's good. You should look, the bare minimum from this is you should be able to look at a Lagrangian and know what's going on. Okay, that's like any physicist, not even theoretical physicist, should be able to do that. Okay, at a bare minimum. What is this theory saying? That's good. You found a mistake. Okay. Lord knows I've written tons of Lagrangians. I once wrote a Lagrangian. We had to like come up with a supersymmetric theory. So I wrote down the Lagrangian. My professor wrote, the universe doesn't exist in this theory. And like only in a physics class can this be the natural comment on a problem set. Okay, so now I'm going to take a detour and we are going to talk about the Feynman rules for non-abelian gauge theory. Oh, I didn't give you your homework. Wow, I didn't write down any homework. Okay, your homework is just the reading and the overlay. So Srednicki 68 to 72. Okay. Sorry, I forgot. Or you guys don't mind, but. Okay, so first of all, what's the Yang-Mills Lagrangian? So L Yang-Mills is minus a quarter. Right, this is E mu nu, where E is the color factor, right? Actually, this should really be minus a quarter trace of F E mu nu E mu nu, where E are the color factors. Okay. So what I want you to have in the back of your head, as we do this, I want you to have a higher dimensional Lagrangian. So we'll call this L Yang-Mills 6, because this is a 6 dim operator. That would go like minus a quarter F. Well, you would have A, B, C, D, E, F. You'd have like a G. But we'll call this a G. It doesn't matter. G mu nu F G rho mu FG rho mu, right? I want you to have in mind some Lagrangian that looks like that, with the trace, right? Sorry, forgot the trace. And I want you to work out the Feynman rules for that, okay? Very annoying, but you have to do it. Okay, so you keep that in mind as we move through this. Again, one can do it in sort of the really, I'm not going to derive the rules for you, okay? I'm just going to show them to you. But there's many ways to derive Feynman rules. You can do it in the Wick contraction, generating functional way where we did that. You should know how to do that. Everyone should know. But like you can, in principle, get Feynman rules from looking at a Lagrangian. Okay, that in principle. All right. Okay, so what does this equal? I'll give you a second to work that out. Do we know what F mu nu is? It's not what you think it is. It's not what you think it is. So what you will see is that F mu nu is d mu a mu minus d mu a mu plus G. See, these need color factors. A, F, A, B, C, A, B, mu, and C, mu. And what you'll find in that is this comes from taking the trace. Oh no, sorry. Oh my gosh. This is the trace of F mu nu. Oh my gosh. Oh my gosh. And F mu nu then is d mu a mu a minus d mu a mu a plus I with FABC. Okay. So now you multiply this out. So I'll give you a second to work out the top while I think about it. Okay, so you'll get like -1/2, but let me just d mu, d mu, d mu, a d mu. G F A B E. Mu A B mu. What do I want? An index on the derivative. Yeah. The contraction. Wow, Jen, I can't believe my nu look like a J. Mine's order. ABE, CDE. I'm just multiplying this out. I'm not really doing anything fancy. You can get the same result on your own. Okay, that's what you get. Now okay, let's just say you get, now, okay, I need to gauge fix this. I'm not gonna do that, it's annoying. You just get an extra term. I'll just write down the gauge fix term. Actually, forget it. I'm not gonna gauge fix this. Srednicki will gauge fix it for you. It seems kind of silly for me to do it because I don't even like that gauge. First of all, we don't even use the gauge. Srednicki admits this. He says, oh, the more conventional gauge is discussed in chapter 82 or whatever, when he talks about scattering amplitudes. So yeah, so let's not bother. Notice now, so like, okay, let's think about this. I have a G squared term. So okay, so let's just talk about how we can get Feynman rules very, very briefly. A G squared term is going to give me what? It's going to give me a 4-point gluon interaction. That would correspond to a square term in the coupling, right? This is just now like what we did in perturbation theory with the S matrix, right? So that's what I mean. In principle, you're getting the same kind of thing, expression. The G term is going to correspond to a 3-point coupling. Okay. So now you're going to get an analog for this in F cubed. Okay, and then you have to work out it's not going to be the same. It's not that easy, but you see, this will be your first step, and you'll get like 45 terms in the algebra, and you'll work it out. Okay, so these are what's going to correspond to the vertices. Anything that depends on G, right? Because G is an interaction. So it's going to give us vertices, right? Vertices are interactions. Okay. These guys are going to give us a propagator. Oh, not this. These guys are going to give us a propagator. Okay. So let's write down the propagator. I'm not going to derive this. You will do it. You will see how to do it. But I want to give you the Feynman rules. You see, these are the kinds of things where Lancaster-Blundell kind of falls short. They don't really like go in depth with some of the more modern topics. So Okay, so the propagator in non-abelian gauge theory. So there's our little delta. So it has color factors, and it's dependent on some internal momenta we'll call K. Is delta AB K squared minus I epsilon. That's just the standard prescription. G mu nu minus K nu over K squared, where G mu nu is the Minkowski metric. And note, if I gauge fix this, I would get an extra term here. Okay, that's really the only difference. So that's the propagator. At tree level, this is extremely simple, right? Nice analytic structure. You just have poles and at K. Okay, let's draw the vertices. So you could have like a 3-point thing that looks like this. So what am I really doing here? So wait a second. Wait a second. You would draw. Right. No, see, I'm setting myself up for failure. This is going to be easy to draw a 4-point interaction. And that looks like that between gluons. So each line now is going to have a momenta, called this P, and then a space-time index and a color factor. Okay. So 3 degrees of freedom now. That's the main difference. So I don't know, call this K, call this nu, call this B for the color factor, and all the momenta is flowing outwards from the vertex, right? Obviously. Right, because if it was flowing inward, you'd have some, well, it could be flowing inward. It could be flowing inward, okay. Gotta be careful there. I don't know, call this Q, call this rho C, and then call this, you know, for Jenna, we'll call this J, okay? No one calls momenta J, but, and we'll call this sigma D, okay? That's the 4-point interaction. And the 3-point interaction is the same thing, just with 3, okay? So I drew you a Feynman diagram today. Don't tell me I didn't. Oh no, wait, I drew the vertices too, so never mind. I drew plenty of Feynman diagrams. Okay, and the vertex will go like I, B, A, B, C, mu, nu. So this is going to be the 3-point vertex, right? Because I have 3 color indices. And it's going to go I minus G, F, A, B, C. Again, coming from the G term in the coupling. Times minus I R mu, G mu rho. And if let's just write out the full expression for the vertex. So we're going to get a G, F, A, B, C. Q minus R mu, G mu rho. Plus R minus P mu G mu rho. So I'm just taking now, I'll say it at the end. Let me just write down the full expression. Plus P minus Q rho G mu mu. So this is it. This is the expression, but like, let's just talk about it. So basically, I've taken all the different permutations of the momenta, which you should do, okay, and exchange them. So this would have what? I think 5 more. So I'll just write plus perm. So you take all the permutations. I think I got all of them here, but or all the non-vanishing ones. Okay, I'm not going to write down the 4-point vertex. It's a pain in the ass. It's really long. But I'll give you the schematic. So you're going to have now some I, V, A, B, C, D, mu, nu, rho, sigma for the 4-point vertex. And you're just going to have what? You're going to have some I, G squared, G mu, nu, G rho, sigma, plus dot, dot, dot. Okay. You'll have all permutations of the metric. Okay. That's the schematic. Okay, great. So it's not too bad. It's just, it's just more stuff you need to keep track of. That's what I think. You see, that's what I think it all comes down to. You start with scalar field theory. There's no stuff you need to keep track of, right? Everything's identical. There's no indices. It's just straightforward. Then you go to QED. Then you have to keep track of different spin statistics, right? Now the fermions give a minus sign and spinors, and then you go to gauge theory and then non-abelian gauge theory, and then you have color. It's just kind of like building the machinery. It's not really too mysterious. Okay. Okay, a quick word on loops. So this might be something you want to look into. So if you want to look, so obviously these are the rules at tree level. There's a very special thing in, good, we have a lot of time, perfect. I'll get through my anomalies argument. There's a very important thing to look at in QCD when you're talking about loops, namely this object called ghosts. Okay, I'm not going to go into that here, but you should read about it because it will be important for our future study. In particular, Faddeev Popov ghosts, named after the two people that kind of came up with the idea, which again are, they're artificial things to get rid of infinities. Okay. That's like what they are. They're virtual particles. Okay, since we are all kind of like, let me write down the Quark Lagrangian, right? Just so we have it. So the Quark Lagrangian goes I, psi bar I, Bij slash psi bar j. This should look familiar from the Wilczek article. Minus m psi bar I, psi bar j, right? So that's the free Quark Lagrangian. Okay, I will just work this out for you. So you get an I, psi bar I. I'm just going to work out this d slash so we know what it is. Gamma mu d mu psi I. Minus m psi bar I psi j. Oh, sorry, this should be a psi j. Plus G A mu psi I. Or psi bar I, gamma mu TA I j, psi j. Sorry, these should be I's. Because, and then you can write one for the J's, because this will take care of that term. So that's what that should look at. Where T is your standard generator, right? SU3 generator. Okay, the Quark vertex factor is I mu A I j plus I gamma mu T A I j. So what's the difference now between the Quark Lagrangian, sorry, IG. What's the difference now between the Quark Lagrangian and the regular non-abelian gauge theory Lagrangian? Well, we have these generators popping up, and we also have some spinor stuff coming in to the story, right? And let me just write down the Quark Lagrangian, the propagators, so we'll call it Sij. Just so you have these expressions. They're useful to have when you're doing little calculations. Minus P plus M, if you want to compute a little Feynman diagram or whatever. P squared plus M squared minus epsilon. Delta ij. So this looks very familiar. It's basically a fermion propagator, right? Just with this extra delta ij. Okay, so that's all for the Feynman rules. So that's why I said this would be a quick detour. I just want to make sure we all have the same expressions because there's tons of this stuff online. And I don't want I don't want us all to have different expressions for a propagator. That would be annoying because there's all different gauges on things one can work in. Okay, great. So now we're going to go to anomalies. So does anyone have questions about any of this? Please don't ask me what a quark is, okay? I don't have like 6 hours, so we can talk about that tomorrow. Okay, let me erase. Beautiful. I think in the Wilczek article, when he writes down the Quark Lagrangian, he uses mu's and nu's. You can do that too. Doesn't matter. Okay, let's talk about anomalies now. Okay, that's really the topic I wanted to start today with, but since we're kind of behind, it's okay. So pretend this is the start of the lecture now. So welcome to week 19. What is an anomaly? So it's very funny because sort of at the beginning, I'm going to ask you a question and I want your answer. If you have a classical symmetry, okay, let's say you have a rotational symmetry or translational symmetry, whatever, would you expect it to hold at the quantum level? That's the question. Isha, what do you think? Just naively, I mean, what would you expect?
Yes.
Okay, right? In principle, I mean, why would, right? I would expect it to hold. So in other words, let's say I had some classical symmetry. So I have like phi go to phi plus delta phi. So this is a classical symmetry. Right, so this leaves the action, the classical action invariant. So right, so S of phi equals S prime of phi plus delta phi. That's what I'm saying. I also say that then this would leave the quantum action invariant. So that is the basic idea. Sorry, that's not the basic idea, but that is the basic premise. And for sort of the first 20 years of field theorists took this for granted. This is life, you know. And yeah, until it wasn't. Okay. So what is an anomaly? An anomaly, and so they were so creeped out by this that certain classical symmetries did not hold to the quantum that they called it an anomaly. Okay, that's like crazy. Okay, so that's what an anomaly is. Now we have to see how they work, okay? And we're going to do it in sort of a Feynman diagram way. Who talks about, every book talks about anomalies, okay? So look in any QFT book. Okay. Right. Okay, so we're going to see this explicitly, okay? And we're not going to finish it today, but I'm going to set up the problem. Okay, so let's just start off with a single massless fermion. Okay, so very simple. Okay, and then the Lagrangian, very simply, is I gamma, no. Can you believe it? I can't even write down the Lagrangian for a single fermion. Psi bar I gamma mu d mu psi. There we go. I still got it. Okay. Okay, so that's for one. So we know, first of all, this has two global symmetries. Psi can go to e to the I theta psi. And we also can write this down with psi having an axial symmetry, okay, from the weak interaction. So now we know this thing has two symmetries. Okay. Now, what do you do? Like, what does this, the student do, the quantum field theory student? They say, okay, my first step, I have a Lagrangian, I have symmetries. I write down what? What should you do as a quantum field theory student? What's the first thing you should write down? Conserved currents, right? That should be your first inkling. So we write down the currents. So in this theory, it's extremely simple. J mu is just psi bar gamma mu psi. And then I also have a conserved axial current, J mu phi. And this, I'll put the 5 downstairs. And this very simply, again, is psi bar gamma mu gamma phi psi. Okay. Am I out of time? No, I have plenty of time. 20 minutes. Okay. Okay, and then what does the intuitive QFT student say? The current is conserved. Noether's theorem. So this just gives me what we always write down. D mu J mu equals 0. And now, but now I have a conserved axial vector current. Okay, so this is like the basic kind of thing we do. And of course, this leads to an equation of motion, I gamma mu d mu psi. Okay. Nothing crazy here. We have a very basic Lagrangian and we're kind of probing what we've always done. Everyone okay? If this is a mystery to you, watch lecture 3, I think. I think lecture 3 is the most useful, where we talk about conserved currents and all that kind of stuff. Okay, I'm going to erase. I feel like any quantum field theory class, the first semester, QFT1, you learn scalar field theory, Feynman rules, symmetries. Those are the big 3 topics, and maybe the basics of renormalization. That's it. So like symmetry is such a big part of any first QFT class because it's so important. Okay, so let's write down something that's going to illustrate this problem. Okay, so I'm going to write down now an amplitude, okay, where I have 2 separate processes. I have a particle, well, not 2 separate processes. I'll draw you a Feynman diagram, okay, I promise. You have a particle at x1, it goes to x2, gets annihilated, goes up to another point, it just keeps moving around in some loop, okay? Okay. So the amplitude is generated now by some current that looks like this, time-ordered current, okay? So it's going to be generated by some current at 2 space-time points, J mu x1. Okay, so the axial current can generate a particle or a fermion. Well, we're going to say fermions. J mu of x2, right, axial current. So the source current at x1 is a regular current, and then at x2, when that fermion annihilates, the axial current generates the particle. whereas this current generates nothing. By the way, you may have seen in the document, I'm doing a lot of calculations that look like this. So this is, maybe you should start, reading about it. It's turning out to be a very useful way to do calculations. Although the one I put in the document was kind of hard. It took me a few hours to find that integral formula. Just saying, like I didn't know how to do that. But okay, so something like a transition amplitude that looks like this would correspond to the following diagrams. So these are like triangle diagrams in a closed loop. Okay, and you have gamma mu, gamma nu, gamma lambda, gamma 5, right? So these are just the currents that are generating the fermions at each space-time point. Gamma mu, gamma nu, gamma lambda, gamma 5 at the corners. And then of course you have the flow of momenta. So you'll have P minus Q at each vertex. There's momenta flowing. P minus K1. We'll call this P minus K2. P minus Q. And P. So these are our two diagrams. So the particles sort of going in a loop. Okay. And so now we just have to write down the amplitude. So let's write down the amplitude. So we'll call this delta lambda mu nu, okay, because we have 3 indices we need to keep track of K1 and K2. Okay. Have -1, I cubed, we have 3 vertices, no coupling. Okay, they're just kind of getting annihilated and created at each space-time point. B4P, 2 pi to the 4th, basic thing. Trace. So I'm using the trace rules. Gamma lambda, gamma 5. So you can work this out on your own. Use the Feynman rules for fermions just without a coupling because it's not important. 1 over P slash minus Q slash. That's because remember, these guys are all internal lines now. Okay, so they're each going to give you some propagator to itself. They're all functioning as internal lines of momenta. Okay, so all I'm going to get, I mean, it's a simple expression. Now I'm going to get another sort of propagating term because all of these lines that form the triangle are like internal momenta. So I have P minus K1, and then you guessed it, I get a gamma mu 1 over simply P slash. All right, and I have 2 diagrams, so I just need to get the other diagram. It's the same thing. Gamma lambda gamma 5, 1 over P slash minus Q slash, gamma mu 1 over P slash minus K2, gamma mu 1 over P. So that's the amplitude with all the trace rules distilled. So this is basically what we need to compute, right? This is what we want to compute. I won't do it. I'll do it next time. This is really annoying, but let's just distill the problem now. How are we going to show the anomaly? Okay, so let's talk about it. Okay, so we know, so classically, d mu j mu equals d mu j mu 5 equals 0. This is a classical symmetry, correct? What is the quantum analog of this? Starts with a W. Like, okay, so, right, so let's slow down. I know this holds classically. Okay, you can show this. If I want to see how this classical symmetry carries over into the quantum realm, what am I going to try and show? What expression am I going to try and verify? Starts with a W. W, A, R, D, the ward identity. So we want to show that the corresponding ward identity is 0. So that's what this equivalency comes down to. Okay, so quantum means I want Noether's theorem, J mu, D mu, J mu. What is this going to go to? K1 mu delta mu nu lambda will equal 0. And K2 mu delta mu nu lambda must equal 0. So this is the ward identity, right? And then the analog of D mu J mu 5, the analog of that, well, only the lambda index is generated by an axial current. Oh, sorry, give me a second. This should be, I think this, well, okay, this should be axial. So this should really go here, right? Because that's generated by the axial current, my mistake. Okay, but of course, Q lambda delta mu mu lambda equals 0. So that's the whole name of the game. Can these word identities hold? And if they don't, we have an anomaly. Okay. Newsflash, they don't. Okay, so then the question becomes, what physically does this mean? And so what this all comes down to is computing this, these divergences, or in other words, working out this integral, which we need some very nifty techniques to compute this integral, Wick rotations and shifting variables, and we'll do that next time. It's a very nice, for me to work this calculation for you is going to be a very nice example for you to see some techniques to work these expressions. So I will leave it there because the next step would involve me computing this, and I think it's better if we save that for next time. Okay, any questions for me, or comments, or concerns? So this is the basic problem of the anomaly, and I think this is the best way to see it, by really working out a Feynman diagram and actually like seeing it explicitly. People do it different ways. By the way, just really quick, this is the reason why chiral gauge theories cannot describe physical reality. They have anomalies everywhere. So if you want to go on Google and look up chiral anomaly, it's a very famous example. Obviously, it doesn't come from this simple example, but it's a famous example of how this sort of makes us get rid of a theory or a physical process. Okay, all right, I'll stop recording. I don't know if Johnson's nice enough to give you a little break. He's nice enough. If he's not,